Welcome to lesson number 4 of the neural network section. Previously we discussed how a line can be used to separate data into discrete classes. This line is found based on previous data sets that have already been labeled as either healthy or sick. This sets up a predictive model that can help us predict the labels of new, unobserved data. In our case, we developed a model that predicts the person's likeliness of being diabetic. And from that model, depending on that person's age and blood sugar, if the coordinate lies above the line, then they're likely diabetic, otherwise not. Let us now approach this a little bit more analytically to make a prediction. First, two inputs are processed. The first one is age, which will be denoted as x1, and the second one is the blood sugar, which will be denoted as x2. Accordingly, the horizontal axis corresponds to the variable x1, and you're probably used to the vertical axis being labeled as y. We're going to label it x2, so as to stay consistent and properly denote the second input variable. Right now you and I can eyeball this data and draw a boundary line that separates the two regions considerably well. Eventually we'll implement an algorithm that's able to find this line on its own with minimal error. But let's assume that through hundreds of iterations, our learning system determined that this line best separates our data into discrete classes. We can now use this data to classify new data as either healthy or sick, depending on whether or not the data point falls below the line or above it. This line's equation can be represented as x2 is equal to negative 0.05x1 plus 12. You're probably used to representing the equation of a line as y is equal to mx plus b. Well, this is the same exact thing as y is equal to mx plus b. That is, where y would equal 0.05x plus 12, but it's important that we follow this notation instead so as to properly reference our input variables. What we'll do now is actually rearrange this linear equation by bringing x2 over to the other side, where 0 would equal 0.05x1 minus x2 plus 12. This is still the equation of our line, just rearranged, and the reason why we did this will be very clear momentarily. Let's take this equation, and if you take any point that's above the line, sub it into the linear equation, where in this case x1 is 80 and x2 is 10. Subbing this into our line's equation, we get a negative number. Similarly, if you take any point that's below the line, where in this case x1 is 20 and x2 is 5, sub it into the equation and notice that you get a positive number. This linear model, which we were able to develop based on previous data sets, its equation can be used to determine the score. If the person's score is positive, such that it's greater than or equal to 0, they likely are not diabetic. Otherwise, if the person's score is negative, they likely are diabetic, thus separating our data into two discrete classes. Let's recall the distinction between the label and the prediction. These datasets, they've already been labeled as either red or blue. They have been given a correct output as having diabetes or not. The goal is to use these labeled datasets to train an algorithm to develop a linear model that can accurately classify this data. Initially, the algorithm starts with a random line with some random equation. Notice that x1 and x2 are multiplied by two constants. These two constants are called the weights, which essentially dictate the slope of the line. And this here is known as the bias, whose value dictates where the line intersects the vertical axis. Different weights and biases will result in different slopes and inclinations of our line, as clearly shown. Generally, the equation for a linear model will be written as w1x1 plus w2x2 plus b. What our algorithm will do is look at the initial data that's already been labeled. It will start with some random line to try and classify our training data, a line like this one. Clearly this linear model is not a good one. It misclassifies a lot of the points. Its classification accuracy is not good, and thus its error is very large. What our algorithm will do is it will keep adjusting the weights and biases of our linear model until it comes up with the optimized line that best classifies our data, the line with minimal error. Our algorithm just made use of labeled datasets to train itself and come up with the perfect linear model. Let's assume this linear model has the following equation. We can now confidently use this model to predict the label of new data points. We do so by first determining the score. Suppose we have a person who's aged 40 years old with a blood sugar of 2. We'll then take the linear combination of these inputs, which results in a score of 8. And now we can make a prediction. The prediction is denoted as y hat, which says that if that person with some age and some blood sugar, if the linear combination of their inputs is greater than or equal to 0, if they're positive, they are classified in region 1. Otherwise, if their linear combination is less than 0, if it's negative, they will be classified in region 0. In our case, the score of a person aged 40 with glucose levels of 2 millimoles per liter has a positive score, and thus they can be categorized in class 1 as not being diabetic, which makes sense in the case of this line's equation, since anything above the line will have a negative score, anything below a positive score. The entire focus of this section will be to train an algorithm to come up with a line whose predictions are accurate with data points that have already been labeled. That is, it must be able to correctly classify all the data points with maximum accuracy. There's one more concept we have to understand before we implement this into code, and that is the concept of perceptrons. Let's talk about that in the next lesson.